Hello, everyone. Now I present the paper Assumption-Based Runtime Verification of Infinite State System by Alessandro Cimatti, Chun, Tian, and Stefano Tonetta. The traditional runtime verification, the runtime monitors are synthesized from a specification or property, like ITL. The monitor returns the verdicts indicating if the input trace violates or satisfies the properties. And in the assumption-based runtime verification, the monitor can be synthesized from also a system model used as assumptions. And besides the existing verdicts, we added one more edicts indicating the trace has go beyond the assumptions. And the partial observable traces can be naturally supported, and also the monitor can be reset to evaluate the specification at other positions in the trees. This is monitor synthesis process. In 2019, the same authors have given the BDD-based algorithm and tools for the assumption-based runtime verification on finite state system. The present work is about infinite state system. The main idea is to reduce runtime verification by model tracking, and possibly also use first order quantifier elimination. We use the relative fast and incomplete bounded model tracking before other more complete full model tracking algorithms. And we use incremental bounded model tracking as an essential optimization of this process. Some preliminaries, the fair transition systems are used to present the RV assumptions as a model and translations from linear temporal logic. And our support of linear temporal logic is basically following the traditional propositional case, except that the atomic can be not any quantifier-free formula from a given theory. And in this work, we support LRA mainly. The ABRV LTL semantics is defined in the following way. If the set of fair passes compatible with the trace prefix is empty, then the monitor returns out of model. Otherwise, if all the possible extensions of the traces compatible with the observation make the LTL property satisfied, then the monitor gives you conclusive true. And similarly, if all the extension of the observations make the property, the negation satisfied, then the monitor shows conclusive false. Otherwise, the monitor says inconclusive. This is an illustration of how assumption-based RV works. For any model used as an RV assumption, we can partition all the possible traces from the alphabet into two parts. One belongs to the language of this model K, and the others are not. And for all the traces, each time the prefix of the observations try to filter them for the next stage. If they do not satisfy the observation, then those traces are ruled out of the consideration. So the traces keep going through the observations. In theory, they become smaller and smaller. And finally, in this example, only two traces remaining here. The actual system follows one of these traces, but we don't know which one is the actual one. If for the possible infinite extension of these traces, if they all make the LTL property satisfied, then in this case, we say the monitor after the first 5 observations will give conclusive true. Similarly, if they all go to the negation of the property, then the monitor will return conclusive false. And if some of them goes to 5, others not 5, then the monitor says inconclusive. And in the extreme case, if after the observation, they go to some of them, they go to the down part outside of the model, then the monitor shows error or out of model. Our first algorithm tried to reduce the runtime verification to model checking. We do this by first construct a model from the prefix of the observations. And this constructed model, after synchronously composed with the assumption, they can be used for model checking purpose. We found that if we do 2 model checking problem, and depending on their results, we can get the corresponding monitor output following our definition of this monitor function. And similarly, we can also reduce model checking problem to runtime verification. Consider how to compute a model checking problem of this one by monitoring. We use empty trace to feed into the monitor, and depending on the output of the monitor, there are 4 possibilities. And in fact, the model checking problem is true if and only if the monitor output is conclusive true or error. In the second case, actually the model of the model checking problem is empty, but this is usually not the case. The conclusion here is that the ABRV problem with infinite state assumptions is undecidable, simply because the infinite state model checking problem is undecidable. The forward image in a fair transition system can be defined in this way. Given a set of states and a transition relation, the forward image can be expressed as a formula like this with first order existential quantifiers. But we need to sometimes we need to send the formula to SMT solvers, which only accept formulas without quantifiers. And this is why we need first order quantifier elimination to translate this forward image into an equivalent quantifier-free formula. Our next algorithm is essentially a dual version of the previous one, but it tries to maintain two belief states between the quantifier elimination and the model checking. And in this algorithm, the input observation can be processed incrementally. The procedural code is in our paper, but the point is now we do 2 slightly different model checking problems, and depending on their results, we can immediately get the monitoring output. We have some optimizations of the previous 2 algorithms. These are some ideas. if the monitor has reached the conclusive verdict, then for the next input, we don't need to do two model checking, just the one should be enough. And before calling the model checkers, we can use SMT tracking to track if the formula is literally unsatisfiable. And when using the second algorithm, the same LTR property, the false, are always used in the model checking. So internally, we can first translate it into an equivalent fair transition system just once and repeatedly use them later. And before calling the model checking procedure, the full procedure, we can call the bounded model checker in an incompleted way, which returns only counterexample. The idea of incremental bounded model checking is the following. Because all the models used in during the monitoring for model checking procedure, they only differ at the initial condition. This parentheses means that we change this model by replacing the initial condition by a new one. And this initial condition is given by the belief state repeatedly calculated by forward image. The belief states can be represented by recursively in this way. For the first observation, it's the initial condition conjuncted with the observation itself. For the rest of them, we first do a forward image for the previous belief states and then conjuncted with the next one. We found that this SMT formula with the unrolling of the observations, they are equisatisfiable with the belief state of all the involved observations. And the algorithm works by some new procedures. First, we initialize the internal BMC solver to track the non-emptiness of a belief states. And it needs some internal slots to hold the initial condition and some other parameters. The top level BMC monitor looks like this. We first do LTR translations for the original and the negated properties, and we initialize the emptiness tracking process using the transition relation and the initial conditions from the model and the properties. Then, for each new observation, we repeatedly update the non-emptiness for the new observations. And same as before, we decide the monitor output based on the emptiness states of the two parts. And all the complexity is inside this procedure, update and non-emptiness. In this function, we basically followed the bounded model checking algorithm. The difference is that before doing the SMT solving, we inject new observations into the problem encoding. And during the before doing the SMT tracking with the ending term, we first track if the current encoding without ending term is already unsatisfiable. If it is, then the procedure immediately returns, showing that this current belief state is actually already empty. And we also need to keep a window window size to make sure that the unrolling of SMT encodings do not exist after do not go arbitrarily large. And if it happens, we need to call the procedure compute belief state to comprise them all together into a new single formula as the new belief states, and reset the internal states to start for the next round. And finally, if the bounded model checking procedure couldn't give us a conclusive answer for the emptiness of belief states, then we need to call the IC3IA model checking procedure, which is unbounded, but essentially still undecidable. And the procedure compute belief state, it is the only function where we actually call the quantifier elimination. We simply loop over all the existing observations and compute the forward image and the conjuncted with the observation itself. These tools, the algorithm are implemented in the new version of our tools. We have some performance tests. The details can be found in the paper. So basically, we try to use Dwyer's LTL patterns and try to convert the original propositional LTL formula into a equivalent one with some real and integer variables. We use RV assumptions to make sure the monitor shows different verdicts in within the certain steps. And the test has shown that our first algorithm with only reduction to model checking is quite slow. But once we use the quantifier elimination, the performance goes to about 10 times faster. The optimized version is always better than the one without optimization, of course. And finally, by using incremental BMC, the performance of these monitors again is improved, and eventually it is over 100 times faster than the first one. For some conclusions, our ABRV framework now has been extended to support the infinite state system. We try to reduce the problem to model checking, SMT showing, and we also use quantifier elimination procedures. And the support of LTL, the theory, the kind of variables involved in our LTL formula is essentially supported by these underlying procedures. And by using incremental BMC, the performance of the monitor has been greatly improved. And due to the use, because the quantifier elimination doesn't guarantee the boundedness of the output. So essentially, our algorithm cannot be memory bounded, but this seems to be inevitable for infinite state monitoring. These are some future directions.